Hello, everyone, and thank you for coming to my talk today. My name is Gila Agajari, and today I will talk about our work, Decomposition of Response Time, to give a better prediction of children's reading comprehension. Our work is motivated by the predictive power of response time in student modeling that has been used to predict student performance and also to identify and understand different cognitive states that students might be involved with while learning. It is often used based on a sequence of action that students are involved with and the time spent between them to identify different cognitive states that a student might fall into. But something that is less explored is that a student can go through different cognitive states even within a single response time period. So for this work, we hypothesize that response time can be divided into different harmful and helpful subcategories, and identifying this time period within a response time may improve student performance prediction as well. So, we divide the possible cognitive states into three categories of productive thinking behaviors, such as reflection or self explanation, and gaming behaviors such as systematically guessing and also help abuse, and unproductive behaviors such as being in wheel spinning state or mind wandering. And our hypothesis is that using these time periods separately instead of response time as a whole might predict student performance more accurately. So to test our hypothesis, we will use data gathered from an iPad application named Embraced, which is designed to improve native Spanish speaker children's reading comprehension in English language. And students read storybooks that is presented to them on the corner of the screen. And they also can see some images related to those stories. In the full version of Embrace, they are asked to move these images as well to demonstrate the text to understand the story better. They can also tap on a word to request for help, and this way they can hear the pronunciation of the words. And when they are done with the sentence, they can press this next, and the next sentence will become readable for them. And in this context, response time is defined as the time a student spends on a sentence. For the purpose of our work, though, we focus on data gathered from the control version of Embrace, because in these versions, actions are limited to reading a sentence, or requesting help, and also pressing next to proceed and go to the next sentence. And the reason is that this restricted set of actions can enable us to focus on the role of response time better. We have access to two data sets that we collected from two experiments with Embrace. Our first data set includes 21 Spanish-speaking students who are from second to fourth grade. They read 7 books in 35 chapters. And we ended up having 716 unique student chapter pairs in that dataset. Our second dataset includes 24 native Mandarin speaker children who are from 7th to 9th grade. And they read 4 books in 20 chapters, and we had 479 unique student chapter pairs in that dataset. In our work, we use 4 measurements. We have a student decoding ability that is assessed by the score that a student gets from decoding part of a test QRI that we present to them before the experiment. We also have a comprehension assessment test within Embrace itself that includes multiple choice question at the end of each chapter that students need to answer. We also measure sentence difficulty, and for that, we use Flesch Kinsey readability grade level. Um, we have some behavioral measures as well that we captured from the log data, including frequency of help requests and frequency of gaming. Gaming is not directly observed in our experiment, but we count for that whenever a student tries to skip a sentence before reading that. So we divide response time into three main categories of gaming time, reading time, and thinking time. For instance, let's say a student spent 10 seconds on a sentence. An example of decomposition can be 3 seconds on gaming, another 3 seconds on reading the sentence, and the remaining 4 seconds might be unproductive, interacting with the system. So we start with estimating gaming time, and after that we extract gaming time from the response time to get to reading and thinking time. Then we estimate reading time, and the remaining part would be thinking time that we will further decompose to productive thinking and unproductive thinking portions. During the studies with Embrace, we realized that some students try to skip the sentence by pressing on this next button when it was disabled. And they try to skip the sentence. And a student who pressed this button when it was disabled, for them, we calculate gaming time as the time between they first see the sentence until the last time they actually press this next button when it is disabled. So our next step is estimating reading time, and for that we first estimate how many words a student should be able to read based on their grade level. And for that we use Maurice guideline to have access to these reading rates. Then we adjust these reading rates based on two features of the student's reading ability and text difficulty. We create another interval based on QRI score divided by text difficulty, and then we map that interval on reading rate interval to get a reading rate estimate based on these two features. Now that we have these reading rates, and also the word count in each sentence, we can estimate reading time easily like this. So the remaining part of response time after extracting gaming time, reading time, and time spent on help would be considered as our thinking time that we now need to decompose to productive thinking and unproductive thinking. And to do that, we find a threshold in thinking where before that threshold, thinking more result in better performance, but after this threshold, student performance drops. And we estimate these thresholds in thinking time for each specific student and for each specific chapter, like you can see in this figure here. To find this threshold, we use a piecewise regression model with student performance as the outcome and average thinking as the predictor. This way, we have an estimate of productive thinking threshold for each student that we show as lambda student here, and an estimate of productive thinking threshold for each of our chapter that we show as lambda chapter in this figure. Since we want this threshold to be based on both chapter characteristic and student characteristic, we need to combine them. And for that, we build two equations. One equation with lambda student as the outcome and QRI as the predictor, and another one with lambda chapter as the outcome and chapter difficulty as the predictor. Now we can combine these thresholds using the correlation coefficient between QRI score and estimated student level threshold using that we call X, and the correlation coefficient between chapter difficulty and estimated chapter level threshold that we call y in this formula. So now that we have this threshold, we can decide what part of thinking was productive. If thinking is less than this threshold, we consider the whole thinking time as productive. And if thinking is greater than this threshold, we consider the time after this threshold as unproductive thinking time. So we compare our model with two baseline models, one linear and one nonlinear. And here are the set of features that we use in all of our models. And like you can see here in this table, all of the features are identical, except that in our model, instead of response time as a whole, we decompose it to different portions, like I explained. And to see how our method worked, we compared and showed our result here. And like you can see here, our model improved R square metric significantly compared to the other two baseline model, which shows better generalizability ability. And by comparing AIC and BIC, we also show that this result is not due to introducing more features. However, our model didn't lead to similar result when we applied that on our second data set. Our second baseline is better than our model. And one explanation is that in this data set, we didn't have any indicator of gaming behavior, so we couldn't capture gaming time. In summary, we proposed a new method to decompose response time to different proportions based on student cognitive states and showed that using them to predict response time improves the prediction of student performance. And as our future work, we plan to find more accurate way of estimating these subcategories. We also are excited to see how our approach can be applied in different domains. At the end, I would like to thank Arthur Glenberg and Adelia Respirator for her generous help with this study, and also I would like to thank NFS for supporting this work.